Hello everyone, welcome back to Learning as a Hobby. Today, in this video, I'm going to go over my summary for Theodore Shifrin, Shifrin's book, Multivariable Mathematics. We're going to do chapter 3. So let me bring up the notes for that. Okay, this section is on subspaces. So we start with a definition. Okay, so a set V, which is a subset of Rn, is called a subspace of Rn if it satisfies these three conditions. Right, so the zero vector has to be in the subset. Property number 2, whenever V is an element of the subset V and C is a real number or a scalar, we have the scalar multiple C times V is also an element of V. In other words, it's closed. The subset has to be closed under scalar multiplication. And property 3 says whenever V and W are elements of the subset, we have the sum V plus W also an element of the subset. Or in other words, the set is closed under vector addition. Right, so if those three properties hold for some subset of Rn, then it's a subspace. And he gives some examples of subspaces here. Right, so these two subspaces are called trivial subspaces because they're subspaces of every vector space. So trivial subspaces. And then the other ones are maybe slightly more interesting subspaces. So, well, maybe I should at least mention the first two. So the first subspace is the trivial subspace that just contains the additive identity 0, whatever that is. Actually, I think in this book, actually, we're always assuming that these things come from Rn, so it would be the 0 vector. The second example is the entire set Rn. That's also a subspace. Example 3, V is the set of all x in Rn, such that x is equal to t times a vector u for any t in R. For some this should be for any, or sorry, for all t in R, for some fixed u in Rn. Right, so all scalar multiples of some vector. Right. The fourth one is the set of all vectors x in Rn that is a linear combination of two fixed vectors u and v. Right. So st vary over the real numbers, and u and v are fixed vectors. So this is any excuse me, any linear combination of two fixed vectors gives you a subspace in Rn. Right. And example 5. Let any v is any x in Rn, where a times x is equal to 0 for a non-zero vector a in Rn. So any the set of all vectors that are orthogonal to some other fixed vector that is non-zero. Okay. So these are examples of subspaces. We can prove that they are by showing that they satisfy these three properties here. I won't do all of them. That maybe I'll do number 5, just because it's the last one. But you can show that that all of these satisfy those three properties. But let's actually go to the whiteboard, and I'll actually prove one of these. He does prove all of them in the textbook, but like I said, it's very similar. You just show that it satisfies the three properties. But let's try letter 5. Number 5. We'll prove that one's a subspace, just so you can see how it's done. Right, so our set looks like this. Right, so show that this is a subspace. Right, so the proof, like I said, is just showing that those three properties are true. So if we take A times the 0 vector, clearly you get 0. So that implies that the 0 vector is in V. So that first thing is satisfied. 2, let X be any vector in V, and let C be any scalar in R. Consider A times CX. Okay. And using the associative law for scalar multiplication, this is the same thing. Sorry, not associative, commutative law for scalar multiplication. That's the same thing as this, which is C times 0, which is 0. I'm sorry, did I say for scalar multiplication? Sorry, this was a property of the scalar product, which we did in the last section. Sorry. Okay, so that checks out. So therefore CX is in V. Right, and lastly, we have to show that it's closed under addition. So let X and Y be in V. Consider A times X plus Y. Right. There's a distributive law for the dot product. This is 0 plus 0, which is 0. Therefore, X plus Y is in V. So the three conditions are satisfied, therefore it's a subspace. And the other examples you can prove, in the same way. You just show that it satisfies the three properties. Right, so let me go back to the board, or to the notes rather. Right, and he gives some non-examples here as well. Maybe I'll show why. Maybe we'll do the first one just to see why that one at least is not a subspace. And you can try the other two as well to see which one of those three properties fails. So the first example here is the set of two tuples, set of ordered pairs in R2 that have the property that X2 is 2X1 plus 1. So let's actually show that that one is not a subspace. And I'll do that on the whiteboard. All right, show this is not a subspace. Okay, so for example, I can actually take two specific vectors in this set. For example, I can take the vector, let's see, I can pick 1, 3, and, or actually I can choose a scalar multiple. Let's do, say, I don't know, 2x. And let's add them together. I'm sorry, I'm taking a scalar multiple. If you look at 2, 6, 6 is not 2 times x1, which is 2 plus 1, right? So this vector here, even though this vector is in the subset and this is a scalar, the scalar multiple, so 2x is not in the set S because it doesn't satisfy the condition for membership in the set. Right, so that shows that this is not a subspace. Okay, so, and the, like I said, the other ones are, similar. You just show which one of the, if one or multiple of the properties fail. For example, in this one, actually all three fail. The zero vector is not in there. It's not closed under scalar multiplication, and it's also not closed under addition, which you can check yourself, but you just have to show that one of the properties fails. Okay, let me go back to the notes. All right, and like I said, so these are just two other examples he gives of things that are not subspaces. Okay, definition next. Let V1 through Vk be vectors in Rn. If C1 through Ck is an element of R, are elements of R, in other words, they're scalars, then the vector V equals C1 V1 plus dot 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 plus Ck Vk is called a linear combination of V1 through Vk. And the set of all linear combinations of V1 through Vk is called their span, and we denote it by span V1 through Vk. Right, so that's this set here is the set of all linear combinations of those vectors. In other words, if I write this out in set notation, right? So the set of all linear combinations of those vectors. All right. He does talk about some notation here. Usually we use this notation to denote the standard basis vectors for Rn. So for example, actually, let me do this on the whiteboard just because this notation comes up a lot. So for example, in R3, E1 is the vector 1, 0, 0. E2 is the vector 0, 1, 0. E3 is the vector 0, 0, 1. Right? In R2, E1 is 1, 0. E2 is 0, 1. And in R4, E1, oops. In R4, E1 is 1, 0, 0, 0. E2 is 0, 1, 0, 0. And so on like that. And in Rn, E1 is 1 with n minus 1 zeros after it, and so on like that. Sorry, this should be E1. So that's what that notation means. These are called the standard ordered basis vectors for Rn. So this would be although did we talk about basis vectors in this section yet? I don't think we did. But anyway, this notation is useful, so that's what it means. Let me go back to the notes. Okay, the reason that this is the standard basis vectors for Rn is because you can write the vectors as a linear combination of them very easily. So the coordinates here are just the weights in the linear combination for the standard ordered basis vectors. Right. Proposition 3.1. Let V1 through Vk be vectors in Rn. Then V equals span V1 through Vk is a subspace of Rn. Right, that's a proposition, and I prove it down here. All right, so you just, again, to prove that something is a subspace, you just have to show that it satisfies those three conditions. So step number one, the zero vector is in the span because you can write the zero vector as a linear combination of the vectors v1 through vk. You just take all of the scalar weights to be zero. All right, so the zero vector is in there. If you take a vector v in the span, then it's some linear combination of the vectors v1 through v1 through vk, and take an arbitrary scalar in R and look at the scalar multiple. Then, by the way that scalar multiplication works, it distributes over sums. So you get this, which is still a linear combination of v1 through vk. So that means that c times v is in the set, so it's closed under scalar multiples. And similar thing for addition, which I have written down here. So if v is a linear combination of v1 through vk, u is a linear combination of v1 through vk. If you look at their sum and simplify some things using, the algebraic rules for vectors, then you still get a linear combination of v1 through vk. So that means that the sum is in the set, so that it's closed under vector addition. Right, so that means that it's a subspace, right? Because it satisfies those three conditions. Okay, here's just some terminology. If V is equal to span V1 through VK, then we say that V1 through VK span the vector space V, or the subspace V. So there's a difference between the way that we're using span here and span here. So here, this is a set, whereas so here we're using span as a verb. The set v1 through vk span this vector space or this subspace, meaning that every vector in it can be written as a linear combination of the vectors. So in other words, this is a noun and this is a verb. Right. But they sound similar, so it can be confusing. So that's just some terminology. All right, there are two ways in which subspaces of Rn arise. Either being the span of a collection of vectors, which is the parametric approach. We'll talk more about parametric things later on. Or the second way that they can arise is being the set of solutions of a homogeneous system of linear equations, which is the implicit approach. All right, so and we'll have chances to see both of those many times over as we go through the book. So, all right, definition: let V and W be subspaces of Rn. We say that they are orthogonal subspaces if every element of V is orthogonal to every element of W, and we have some notation for that. So this is read V perp, and that set is defined to be the set of all x in Rn, where x dot product with V is equal to 0 for every V in V. Right, so this is called V perp. It's the orthogonal, it's the largest orthogonal subspace with respect to V. Okay. And there's a proposition after the definition. V perp is a subspace of Rn, and since it's a proposition, we want to prove it, but actually he asks us to do that in the exercises, so I'll wait to do that in the exercise video that I'll do next. All right, almost coming to the end of the notes here. If V and W are orthogonal subspaces of Rn, then certainly W is a subset of V perp. And of course, W need not equal V perp. Just to see why that's the case, maybe I'll do this on the whiteboard as well, just so there's space. So if you consider subspace of R3, where V is, let's say, Actually, let's do this even simpler. Let's just use the axes. V is the x-axis, let's say. All right. Then V perp is the YZ plane. Just so you can see why that's the case, let me draw an admittedly terrible picture, but let's say this is the x-axis, this is the y-axis, this is the z-axis in R3. So if you take the x-axis, let me draw it in a different color here. So if you take the x-axis and you look at the set of all vectors that are orthogonal to the x-axis, well, certainly the y-axis is orthogonal to the x-axis, and so is the z-axis, and actually anything that lies in that plane will be orthogonal to the x-axis, right? It'll make a 90-degree angle with the x-axis. Right? So the YZ plane is actually V perp in this case. However, you can have other orthogonal subspaces that are not equal to V perp, but they will have to be smaller than V perp. For example, you could take another orthogonal subspace W equal to the y-axis. Right? The y-axis is orthogonal to the x-axis, but it's not equivalent to V perp. Right? It's a proper subset of V perp. Right? So that's what that last note is saying. Right, let me just go back real quick to the lecture note, the summary. Right, that's essentially the end of the summary for this section. And the exercises that he recommends that we do are these ones, 3, 4, 6, 8, 9, 10, 11, 12. So I have actually already done those. I'll get to those in the next video. So thank you again for watching. Let me just stop my screen share to say goodbye. So thanks for watching. The next chapter is kind of a long one in Shifrin. We'll still be going on with vector spaces and things like that. But it looks like an interesting section, so hopefully there'll be some fun problems in there. The next video I'm going to do, though, is the exercises for this section in Shifrin. Like I said, I'll be doing those problems that I just mentioned. So again, thanks for watching, guys. Please do like and subscribe if you enjoy watching this content. This way YouTube knows to share it with other like-minded people. And it'll, so it'll help the channel grow and help the community grow. So I'll see you guys in the next video, which hopefully I might post the exercise video today as well, because I already have it written up. So I'll see you guys then. Until then, keep learning.